everyone. In this lesson, we're going to continue to solve polynomials, but you're going to learn about the fundamental theorem of algebra. That's going to give you a little bit more information and help you to solve those polynomials. So first we have a review of what complex numbers are. All numbers are complex numbers. We have real numbers and we have imaginary numbers. Included in real numbers are rational numbers and irrational numbers. So sometimes I think it's helpful to just go back and look and remember that when we talk about a complex number, we're referring to all numbers, both real and imaginary. Now, the fundamental theorem of algebra says that every non-constant polynomial with complex coefficients has at least one complex root. And the corollary to that says that if p of x is a polynomial of degree n greater than or equal to 1, then p of x equal to 0 has exactly n roots. So here's some examples of what I mean. If we have x to the first, that's the highest degree term in our polynomial. The degree is 1. We know we have one complex root. If our degree is 2, we know we have 2 complex roots. If our degree is 3, we have 3 complex roots. And if our degree is 4, we have 4 complex roots. So we talked about this a little bit in past lessons. If you have a cubic polynomial, you have 3 roots. If you have a quadratic, you have 2 roots. If you have a quartic, you have 4 roots. And we're just reinforcing it here with the fundamental theorem of algebra. Now, possible combinations of complex roots. Recall from the imaginary root theorem that imaginary roots always come in pairs. So we need to keep that in mind when we examine what types of roots we could have for each kind of polynomial. So let's look at this table. Again, we're looking at a first degree polynomial, and we know that we have one root. If we have one complex root, either real or imaginary, it has to be real because imaginary roots come in pairs. And we know we don't have 2 roots, we only have 1. So if we have a first degree polynomial, we only have 1 real root. That's the only possibility. Now, if we're talking about something like a quadratic, so we have a degree 2, we know we have 2 roots. So we could either have 2 imaginary roots or we could have 2 real roots. Now, for this example, we have x squared plus 1. If I worked that out to solve it, I'd get x squared equals negative 1. I take the square root of both sides, and I'd get x equals plus or minus I. So for this example, we have 2 imaginary roots, but keep in mind we could have 2 real roots. So if I change that problem, let's say I made this x squared minus 1 equals 0. Then I would have x squared equals 1, take the square root of both sides, I'd get x equals plus or minus 1. So you see what I'm saying? In that example, I have 2 real roots. All right, so it's just giving us an idea of what to expect as we're going about solving polynomials. Now, the next one is a cubic polynomial. I know I have 3 roots, so I could either have 3 real roots or I could have 1 real root and 2 imaginary. Imaginary roots come in pairs. I can only have sets of 2, 4, 6, 8, and so on. So for a cubic polynomial, I either have 3 real or I have 2 imaginary and 1 real. For a quartic polynomial, I know I have 4 roots, so I could have 4 real, I could have 4 imaginary, or I could have a combination of 2 real and 2 imaginary. All right, I hope you're starting to get the idea. And finally, just to review, in the last lesson, we talked about the rational root theorem, and that tells us all the possible rational roots. We're going to take all the factors of p, which is our factors of our constant, divided by all the factors of q, which are the factors of the leading coefficient, and that's going to give us a starting point for polynomials higher than a degree 2. So we're going to put it all together and look at some examples. So for number 1, for the given polynomial, we're going to complete the table. So first of all, we're saying, well, what do we know by the fundamental theorem of algebra? Well, this is a quartic polynomial. It's degree 4, so we know we're going to have 4 roots. Now, what could be the combinations of roots we could have? We could either have 4 real roots, we could have 4 imaginary roots, or we could have 2 real and 2 imaginary. We don't know until we start working through the problem. Now, the rational root theorem for this, factors of 4 divided by factors of 1. So this is going to be our starting point, and we would go from there. Here's another example. This time we have a cubic polynomial. So by the fundamental theorem of algebra, we know we have 3 roots. By the imaginary root theorem, we know we're either going to have 3 real roots or we're going to have 2 imaginary and 1 real. And by the rational root theorem for this particular example, we're going to have factors of 2 divided by factors of 1. So this would be the starting point for the possible rational roots. Right, we're going to put it all together now to help us solve a polynomial, and we're just going to use all that information as sort of guidelines as we work through solving. So we have a quartic polynomial, so we know that for this polynomial, we're expecting to get 4 solutions. We're going to have 4 complex roots. And what are the combinations of those roots? Well, we could have 4 real, they could all be real. We could have 4 imaginary, because imaginary roots come in pairs. Let's do or here. Or we could have 2 real and 2 imaginary. All right, good information to have. Now we need to know what's going to be our starting point. What are the possible rational roots? So we're going to do all the factors of 4 divided by all the factors of 1. And when we simplify that, we're going to have possible rational roots of plus or minus 1, plus or minus 2, and plus or minus 4. And now we're going to go ahead and try to solve it. So we're going to start putting these roots, possible roots, into synthetic division and see if we can find one where we get a remainder of 0. So we'll start with 1. And we're going to list all the coefficients, and remember that we need to leave a placeholder whenever we don't have a term. So we're missing a cubic term and we're missing a linear term. So we're going to need zeros as placeholders there. So we're going to have 1, 0, -3, 0, and -4. And for this first guy, it doesn't work. I'm not too happy about that. We're going to have to do synthetic division again, test the next root. So we'll test -1. Right, -1 is also not a root, so we're going to move on to test +2. All right, finally, we found a root that works. So we know that x equals 2 is a root. Now, we started with x to the 4th, and when we use synthetic division, now reduce the polynomial by 1 degree. So what are we left with? We're left with x cubed plus 2x squared plus x plus 2 equals 0. But the same possible roots apply. So we know that 1 doesn't work, -1 doesn't work. We know 2 works. The next root we want to try is -2. So we're going to put -2 in the box. The only difference is now we're going to use our reduced polynomial coefficients. So that would be, in this case, we would have 1, 2, 1, 2. And great, that one works as well. So we also know that x equals -2 is a root. Now this time we started with a cubic polynomial. So now when we write this guy out, we're going to write it as a quadratic. So we have 1x squared plus 0x plus 1 equals 0. And we're going to solve for x. So we get x squared equals -1, and take the square root of both sides. And x is equal to plus or minus I. We have plus or minus 2 and plus or minus I. So we know here that we found 2 real and 2 imaginary, so that would be this scenario here that we have in our table. All right, so hopefully you're starting to see how these theorems can help us. We're going to try another one, and what I would do if I were you is I would pause the video and try this next one on your own. This time we have a third degree polynomial. We have a cubic polynomial, so we know we have 3 complex roots altogether. Imaginary roots come in pairs, so we either have 3 real roots or we have 2 imaginary and 1 real. The rational root theorem, we're going to have factors of 8 divided by factors of 1. And when we simplify that, we're going to get plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. Now we have to start testing till we find one that works. So we're going to test 1 first. The coefficients are going to be, in this example, 1, -2, 4, and -8. All right, we get a remainder of -5, so we know that +1 is not a root. Now we'll try -1. Okay, -1 doesn't work either, so now we'll try +2. All right, finally, we found a root that works. So we know x equals 2 is a root. Now, we started with a cubic polynomial. We had a third degree polynomial. When we use synthetic division and we reduce it, we now have a quadratic. So we have 1x squared plus 0x plus 4 equals 0. So we get x squared equals -4. We're going to take the square root of both sides. We get x equals plus or minus 2i. All right, so let's write those down. Our roots are 2 and plus or minus 2i. So we have 1 real and 2 imaginary. We found this situation from our table. All right, last one, number 3. This time we have a quintic polynomial, a degree 5. So we know we're going to have 5 complex roots. Now this one's going to be fun. You could get a math high off this problem, especially if you try it on your own. The imaginary root theorem tells us that we could have imaginary roots, but they always come in pairs. So we could have 5 real roots. That's the first possibility. Or we could have 2 imaginary and 3 real. Or we could have 4 imaginary and 1 real. By the rational root theorem, we know the possible rational roots are going to be the factors of 24 divided by the factors of 1. Okay, that's a lot of possible roots. So if we were to write them all out, we would have basically just the numerator of possible roots because they're all going to be divided by 1. All right, here we go. So I hope you have your patience all ready. We're going to start with root 1 and we're going to test it. The coefficients are going to be 1, -3, -2, 6, -8, and 24. It doesn't look like we're missing any terms, so we don't need 0 as a placeholder. Okay, 1 doesn't work. Let's try -1. All right, -1 does not work, so let's try 2. Finally, okay, we found one that works. So we know that x equals 2 is a root. Now, we started out with the degree 5 polynomial, so when we reduce it with the synthetic division, we're at a degree 4. So we have 1x to the 4th minus x cubed minus 4x squared minus 2x minus 12. We know 1 and negative 1 don't work. We already used 2, so now we'll try negative 2. Put negative 2 in the box. All right, we found another root that works. So we know that x equals negative 2 is a root. We started with a 4th degree polynomial here, so now we're reducing it to a cubic polynomial. So we have 1x cubed minus 3x squared plus 2x minus 6 equals 0. We're not missing any terms, so we don't need 0 as a placeholder. Now, we've already checked 1 and negative 1. They don't work. We know 2 and negative 2 are roots. The next one to try is 3. All right, we found another root that works. So x equals 3 is a root. This time we started with a cubic polynomial, so now we've reduced these coefficients down to a quadratic. All right, running out of room here. I'm going to put it right here. So I have 1x squared plus 0x plus 2 equals 0. So I have x squared equals negative 2, square root of both sides. So I know that x equals plus or minus I root 2. So my final answer is I have 2, I have negative 2, I have 3, and I have plus or minus I root 2. So if we go back to our table, which one does that match up with? That was going to be 3 real and 2 imaginary. All right, so that's it for this lesson. I hope you enjoyed it. I think these can be really fun and kind of like little puzzles, and it really is a nice lesson where we put a lot of things together. All right, everybody, have a great day.